There is a number that does not make sense. Not in the way that large numbers sometimes feel abstract. Too many zeros to hold in your mind at once. This is different. This number has been confirmed by multiple telescopes, cross-checked by independent research teams, argued over in journals for years, and it still does not fit. The universe, according to everything we understand about how it began, should not have been able to do what it apparently did. Here is what we know with reasonable confidence. The cosmos came into existence roughly 13.8 billion years ago, in a state of almost unimaginable heat and compression. In those first moments, there were no stars, no galaxies, no atoms even, just a scalding plasma of particles too energetic to bind together into anything. The physics of that early universe are not a mystery. We have mapped the faint afterglow of that plasma across the entire sky. We understand, in surprising detail, what the universe looked like when it was only 380,000 years old. And then something happened that we are still, genuinely, trying to understand. Within the first billion years, a period that sounds long but represents less than 8% of all the time that has since passed, the universe went from that featureless plasma to a structured, differentiated cosmos, containing galaxies, stars, black holes, and chemical complexity. The raw material went from protons and electrons to nuclear fusion engines, to supernova explosions scattering heavy elements across space, to new generations of stars forming from that enriched debris, to planets assembling around them. That sequence, on its own, would be remarkable enough. But the details are where the picture gets strange. The first stars that formed were not like the Sun. They were enormous, hundreds of times more massive, burning through their fuel so fast that some lasted only a few million years before dying in catastrophic explosions. Those explosions seeded the surrounding gas with elements that had never existed before: carbon, oxygen, nitrogen, silicon, iron. The building blocks of chemistry, scattered across the early universe by stars that burned briefly and died violently. And somewhere in that same period, black holes were growing. Not the stellar mass black holes left behind by dying stars, but objects millions and billions of times more massive than the Sun. Structures so large that the physics of how they formed in such a short time remains one of the most debated questions in modern cosmology. By the time the universe was 1 billion years old, we can observe, from our position today, galaxies already well into the process of formation, structured, differentiated, chemically complex compared to where everything started. The question is not simply, how did all of this happen? The question is, how did all of this happen so fast? Pull back for a moment and consider the scale of what that first billion years actually was. The universe today is approximately 13.8 billion years old. 1 billion years is therefore a relatively short fraction of total cosmic history, but the misleading thing about fractions is that a billion years is still a billion years. That is a duration 4 times longer than the oldest fossils of complex multicellular life on Earth. It is more than twice the age of the earliest evidence for life on this planet at all. In cosmic terms, a billion years is not nothing. But here is what makes the early timeline feel compressed to astronomers and cosmologists. The conditions in the early universe were simultaneously extreme and deeply hostile to structure. The universe was expanding. It was cooling, but still hot by any reasonable standard. The density of matter was falling, as the volume of space grew, and matter in the early universe was distributed with remarkable uniformity. Not perfectly uniform, but close enough that the gravitational seeds needed to grow galaxies were almost imperceptibly small. Starting from that point and arriving, 1 billion years later, at a cosmos containing 100 billion star galaxies and billion solar mass black holes, the physics required to bridge that gap are not fully understood. Some of the pieces are clear. Gravity works on dark matter in ways we can model mathematically, and dark matter appears to have provided the scaffolding around which ordinary matter clustered. The large-scale structure of the universe, the cosmic web of filaments and voids that we can observe today, traces back to fluctuations in the early universe that we can actually measure in the light left over from that first plasma phase. But the details of the first billion years, the specific sequence of events, the relative timing, the mechanisms that drove the transition from formless gas to structured galaxies, these remain contested. Observations from the last few years, some of them genuinely unexpected, have forced revisions to models that were previously considered well established. The James Webb Space Telescope, since beginning operations, has returned images of galaxies so distant that we are seeing them as they existed within the first few 100 million years of cosmic history. Some of those galaxies are larger, more structured, and more chemically mature than the models predicted. Not slightly off, in some cases, significantly off. That discrepancy matters. It means either our models of early galaxy formation need revision, or our understanding of that first billion years is missing something important, or both. To begin to understand what actually happened during those first billion years, not just the broad outline, but the specific chain of events and the genuine scientific puzzles still embedded within it, it helps to start even earlier than the first stars. Not at the Big Bang itself, which carries its own unresolved questions about what, if anything, preceded it, but at the moment when the universe first became transparent. For its first 380,000 years, the cosmos was opaque. The plasma that filled all of space was so dense and so hot that light could not travel freely through it. Photons, particles of light, were constantly being scattered, absorbed, re-emitted, redirected. The universe was a fog that light could not penetrate. Then the temperature dropped enough that electrons and protons could combine into stable hydrogen atoms. This happened across the entire universe, rapidly, in a transition called recombination. And when it did, the fog cleared. Light that had been trapped, scattered in every direction for hundreds of thousands of years, was suddenly free to travel. It has been traveling ever since. We detect it today as the cosmic microwave background, a faint glow of microwave radiation arriving from every direction in the sky, carrying within it the imprint of the universe as it existed 380,000 years after the Big Bang. That light is extraordinarily uniform. The temperature variations across the entire sky amount to about 1 part in 100,000. The early universe, by the time it became transparent, was very nearly featureless. Very nearly, but not quite. Those tiny temperature variations are not noise. They are structure. They represent minute differences in the density of matter at the moment of recombination, regions slightly denser than average and regions slightly less dense. Those density fluctuations, tiny as they were the seeds of everything that followed. Over the next several 100 million years, gravity pulled matter toward the denser regions. Dark matter collapsed first, because it had no radiation pressure pushing back against it. Ordinary matter fell into the gravitational wells dark matter had already begun digging. Gas accumulated. Clouds formed. The first regions dense enough to trigger nuclear fusion lit up as stars. This period, between recombination and the first stars, is called the cosmic dark ages. No light, no stars. Just a universe of hydrogen and helium gas, slowly condensing under gravity, with no electromagnetic radiation, except the fading microwave glow cooling as the universe expanded. The Dark Ages lasted, by current estimates, somewhere between 100 and 500 million years. The uncertainty in that range is itself telling. We do not have direct observations of it. No telescope yet built can see back to that era, because there was nothing producing visible light. What ended the Dark Ages is the first question the rest of this investigation will follow. The answer seems obvious: stars. And stars are, eventually, the right answer. But getting there, understanding what those first stars actually were, how they formed, how their deaths changed everything that came after. That journey through the first billion years reveals a sequence far stranger and more consequential than the simple picture of stars formed, galaxies followed. The first generation of stars, called Population 3 stars by astronomers, was unlike anything in the universe today. Formed from gas that contained only hydrogen and helium, with trace amounts of lithium, no heavier elements, because heavier elements did not yet exist. These objects could grow to extraordinary masses without the cooling mechanisms that limit the size of stars in later eras. When a modern star-forming cloud contracts under gravity, it radiates heat through atoms and molecules made of carbon, oxygen, and other elements. That radiation carries energy away from the collapsing cloud, allowing it to cool and fragment into the sizes of stars we see forming today. In the early universe, that mechanism was absent. The gas contained almost nothing but hydrogen. It cooled less efficiently. The collapsing clouds therefore fragmented less, and what formed was not a cluster of sun-like objects, but potentially enormous individual stars. Theoretical models suggest some may have reached hundreds of solar masses or more. The implication of that mass is enormous. A more massive star burns hotter, faster, and more completely. A Population 3 star massive enough would have exhausted its nuclear fuel in perhaps 1 million years, compared to the Sun's expected 10 billion-year lifespan. When it died, the explosion would have been extraordinarily energetic. Some may have ended not as supernovae, but as something called pair instability supernovae, explosions so complete that almost no remnant was left behind, only a rapidly expanding cloud of freshly synthesized heavy elements. Those elements, carbon, oxygen, silicon, iron, seeded the surrounding gas. The next generation of stars, called Population 2, formed from that enriched material. They burned differently, cooled more efficiently, could form in smaller masses, and when they died, they left behind remnants, neutron stars and black holes, that seeded the universe with compact objects. All of that happened within the first few 100 million years. Before the universe was 1 billion years old, at least 2 full generations of stars had already lived and died. The cosmos had already undergone a chemical transformation from the simple composition inherited from the Big Bang to something containing most of the periodic table. That is where the story becomes genuinely difficult to follow. Not because it is poorly understood, but because every answer about the early universe tends to reveal a deeper problem underneath it. The first stars ended the Dark Ages, yes. But in doing so, they also began a process called reionization, a wholesale transformation of the hydrogen gas that filled intergalactic space. Understanding what reionization was, how it happened, and when it ended, requires confronting the fact that we currently cannot directly observe the process in action. We can see before it began and after it ended. The transition itself, some of the most consequential chemistry in cosmic history, is almost entirely hidden. And then there are the black holes. Within the first billion years, quasars, extremely luminous objects powered by supermassive black holes, have been observed at distances so great that we are seeing them as they existed when the universe was less than 800 million years old. Some of these black holes have been measured at masses exceeding 1 billion times the mass of the Sun. 1 billion solar masses, in less than 1 billion years, starting from nothing. The physics of how those objects could have grown that large, that fast, starting from stellar remnants of perhaps a few hundred solar masses at most. This is not a problem at the edges of cosmology. It sits near the center of active research, with multiple competing explanations, none of them fully satisfying. To trace the first billion years of everything is to follow a chain of events that begins in featureless simplicity and arrives, with astonishing speed, at a cosmos structured and complex enough to raise questions we are still working to answer. Understanding how that happened, not as a summary, but as an investigation, following the evidence through each transition, requires going back to those first moments when the fog of the early universe cleared, and asking what, exactly, gravity and gas and time actually built. The universe was once nothing but a cooling, expanding sea of hydrogen. What it became in its first billion years is still not fully understood. That is where this journey begins. The universe, at 380,000 years old, had just done something it had never done before. It had become quiet. Not quiet in the way we mean silence. There was no air, no medium for sound to travel through anyway. Quiet in a deeper sense. For the first time since the Big Bang, the cosmos was no longer a churning, opaque plasma screaming with radiation. The temperature had dropped to roughly 3,000 Kelvin. Electrons, which had been moving too fast to be captured by protons, finally slowed enough to be held. Hydrogen atoms formed. Across the entire observable universe, this happened within a relatively narrow window of time, not instantaneously, but fast by cosmic standards, over perhaps 100,000 years. And when it was done, light moved freely for the first time. The photons that had been ricocheting through the plasma for hundreds of thousands of years suddenly found nothing in their way. They streamed outward in every direction. That light is still traveling today, stretched by the expansion of space from visible wavelengths into microwaves, arriving at our detectors as the cosmic microwave background, the oldest light we can observe, a snapshot of the universe, frozen at that moment of clearing. Look at a map of the CMB, and you are looking at the universe in its infancy, and what you see is almost nothing. A near-uniform glow, with temperature variations so small they push the limits of measurement. But those variations exist, and they are not random. They carry a pattern. To understand what that pattern means, you have to understand what was actually happening in the plasma before it cleared. In the early universe, ordinary matter and radiation were locked together, not metaphorically, but physically. The photons and the plasma interacted so strongly that they behaved as a single fluid. When gravity pulled that fluid toward a dense region, the pressure of the radiation pushed back. The fluid compressed, heated, expanded, cooled, and compressed again, oscillating, like sound waves moving through the plasma. These are called baryon acoustic oscillations, and they imprinted a characteristic scale on the distribution of matter in the early universe. When recombination happened and radiation decoupled from matter, those oscillations froze in place. The pattern of compressions and rarefactions became the pattern of matter density. And that pattern, imprinted 380,000 years after the Big Bang, is still visible today in the distribution of galaxies across hundreds of millions of light-years. The CMB is therefore not merely a historical relic. It is a map of initial conditions. Every temperature fluctuation in that ancient light corresponds to a region of slightly different density, and density determined what gravity would later build. The slight overdensities were small. On the scale of the entire observable universe, the early cosmos was extraordinarily uniform. But gravity is patient. Given enough time, even a tiny excess of matter in one region will attract slightly more matter than its surroundings, which increases its gravitational pull, which draws in still more matter. A small advantage compounds. The complication is this. If the early universe contained only ordinary matter, the density fluctuations in the CMB are too small to have grown into the structures we observe today in the time available. The math does not work. Galaxies would have needed more time to assemble than the universe has been old. Something else was providing the gravitational scaffolding. Dark matter is not a dramatic name for a mysterious substance. It is a descriptive name for a straightforward observational fact. There is more gravitational influence in the universe than the mass of visible matter can account for. The evidence comes from multiple independent directions. The rotation curves of galaxies, the way stars orbit around galactic centers, do not match what the visible mass alone would predict. Without additional mass distributed in an extended halo around each galaxy, the outer stars would be moving too fast to remain gravitationally bound. Galaxy clusters bend light from objects behind them far more strongly than their visible mass explains. The large-scale structure of the universe, the cosmic web of filaments, sheets, and voids, matches theoretical models only when a substantial component of non-interacting mass is included. Dark matter does not emit light. It does not absorb light. It does not interact with ordinary matter, except through gravity. Whatever it is, and its precise nature remains unknown, it responds to gravity, and it contributes mass. And crucially, it responds to gravity without being pushed back by radiation pressure. In the early universe, ordinary matter was coupled to photons. When gravity tried to compress ordinary matter into dense regions, radiation pressure resisted. Dark matter had no such coupling. It could begin collapsing under gravity far earlier, even while the plasma was still opaque and oscillating. By the time recombination happened and ordinary matter was finally free to move without radiation pushing back, dark matter had already had hundreds of thousands of years to start clustering. The gravitational wells were partially dug before ordinary matter was even allowed to fall into them. This is why dark matter matters so much to the story of the first billion years. Not as an abstract theoretical component, but as the practical scaffolding that made early structure possible at all. Without it, the seeds in the CMB would have been too faint to grow fast enough. With it, ordinary matter had gravitational architecture to fall into, and what it built, once it began falling, was the web of structure that defines the large-scale universe today. Current best estimates put dark matter at roughly 27% of the total energy content of the universe, compared to about 5% for ordinary matter. That ratio means the universe was never primarily made of the stuff that forms stars and planets and people. From the very beginning, most of the gravitating mass was something else, something that left no light but built the skeleton of everything. So the universe at recombination had two things working in its favor: a set of density fluctuations imprinted in ordinary matter by baryon acoustic oscillations, and a pre-existing gravitational framework provided by dark matter halos already beginning to form. What it did not have was stars. The period between recombination at 380,000 years and the formation of the first stars is the cosmic dark ages, a name that accurately captures how little we can directly observe of it. The universe was dark, not metaphorically but literally. The CMB light was fading. No sources of new light yet existed. Intergalactic space was filled with neutral hydrogen and helium gas, gradually cooling, slowly being drawn by gravity toward the dense regions where dark matter was clustering. We cannot see this era. No photons from it reach us carrying useful information about the gas distribution, because neutral hydrogen absorbs certain wavelengths strongly, and the universe was filled wall to wall with it. What we can do is model it, and the models, constrained by the CMB on one end and by observations of early galaxies on the other, give us a reasonably coherent picture of what was happening, even if the specific timing and the detailed physics remain areas of active research. Dark matter halos grew through a process that was neither smooth nor uniform. Smaller halos formed first. Gravity works fastest on the smallest scales, and then merged, combined, and accreted more material over time. The general picture is called hierarchical structure formation, small structures assembling first, larger structures building from their mergers. Into these dark matter halos, ordinary matter fell. Gas clouds accumulated in the gravitational wells. As gas compressed, it heated. In the early universe, where the gas was almost pure hydrogen and helium, the primary way that gas could radiate heat and continue cooling, which is necessary for further collapse, was through molecular hydrogen. Two hydrogen atoms bonded together form a molecule that can emit radiation at specific wavelengths, carrying energy away from the contracting cloud. Molecular hydrogen is a fragile coolant. It forms slowly and can be destroyed by ultraviolet radiation. In the early universe, before any sources of UV light existed, it formed with reasonable efficiency. But once the first stars lit up, they flooded their surroundings with UV radiation, which tore apart molecular hydrogen and made subsequent star formation in nearby clouds harder. That feedback, early stars making it more difficult for nearby gas to form more stars, is one of the complications in reconstructing the history of the first billion years. The universe was not a passive container in which events occurred independently. Every major transition changed the conditions for the next one. The end of the Dark Ages was not a single moment. It was a process that happened at different times in different places, driven by the formation of the first stars in the densest halos. But exactly when the first stars formed, and in halos of what mass, and in what numbers, are questions that current observations cannot fully answer. The best current estimates place the end of the Dark Ages, the first starlight in the universe, somewhere between 100 and 250 million years after the Big Bang, give or take 100 million years. That uncertainty is worth pausing on, because it reveals something important about how this investigation actually works. We are not reading the history of the early universe from a continuous record. We are reconstructing it from fragments, the CMB, observations of the most distant galaxies, mathematical models constrained by physical theory, and, increasingly, by new observations that sometimes confirm the models and sometimes force revisions to them. The James Webb Space Telescope has pushed the observational frontier further than any previous instrument. It has captured galaxies existing when the universe was less than 500 million years old, some of them at less than 300 million years. The images look, at first, unremarkable. Small, red, faint smudges against a black background. But those smudges contain billions of stars, already assembled, already structured, at a time when the models suggested the universe should still be in relatively early stages of galaxy formation. Some of those early galaxies are more massive than expected. Some are forming stars at higher rates than predicted. Some show chemical signatures, heavy elements in their spectra, suggesting multiple earlier generations of stellar evolution had already occurred by the time we are observing them. These results do not overturn the basic framework of cosmic structure formation. The evidence for dark matter scaffolding, for hierarchical assembly, for the role of baryon acoustic oscillations, that framework is not shaken by individual galaxy observations. But the details of how quickly structure assembled, how rapidly the first black holes grew, and what the earliest stellar populations actually looked like, those details are being actively revised. This is what an active scientific frontier looks like. Not revolution, but refinement. And refinement that matters, because the first billion years set the conditions for everything that followed. One of those conditions, perhaps the most far-reaching in its consequences, was reionization. Recall that after recombination, the universe was filled with neutral hydrogen. Neutral hydrogen is opaque to ultraviolet light. It is also electrically neutral, which means it does not interact with photons the way ionized plasma does. When the first stars formed, they produced enormous quantities of ultraviolet radiation. That UV radiation began doing something specific to the surrounding neutral hydrogen. It stripped the electrons back off the atoms, ionizing them. The hydrogen went from neutral to ionized, from a fog that blocked UV light to a transparent plasma through which UV photons could travel freely. This process, reionization, is arguably the most important phase transition in the history of the universe, after recombination itself. It did not happen all at once. The first stars ionized the gas in their immediate vicinity, creating expanding bubbles of ionized hydrogen around each source. As more stars formed, the bubbles grew. Over time, neighboring bubbles merged. The ionized regions expanded and connected until, eventually, the neutral hydrogen in intergalactic space was almost entirely gone, replaced by a warm, ionized plasma through which light could travel freely. The universe became transparent again, but this time permanently. Observations suggest reionization was complete by roughly 1 billion years after the Big Bang, possibly somewhat earlier, possibly somewhat later, depending on which measurements are weighted most heavily. The beginning of reionization, when the first bubbles started forming, is harder to pin down. The transition from a mostly neutral to a mostly ionized universe likely spanned several 100 million years. What drove reionization is not entirely settled. Early stars, particularly the massive hot population 3 stars, almost certainly contributed. Quasars, which are powered by supermassive black holes accreting material, produce enormous quantities of ionizing radiation and may have played a significant role in the later stages. The relative contributions of stars and quasars, and how reionization proceeded geographically, whether it was patchy or relatively uniform, remain active areas of research. A radio telescope array called the Square Kilometre Array, currently under construction, is designed in part to observe the 21-centimeter radiation line of neutral hydrogen, a specific wavelength emitted by neutral hydrogen that could, in principle, allow direct mapping of where the neutral gas was and how the ionized bubbles grew. That observation, if it succeeds, would give us the first direct window into the reionization era. For now, that window is mostly closed. What reionization changed was not just the state of the gas. It changed the conditions for everything trying to form within it. Ionized gas is warmer than neutral gas. A warmer intergalactic medium means higher pressure in low-density regions. Higher pressure makes it harder for gas to collapse into small halos and form stars. Reionization, in other words, partially suppressed subsequent star formation in the smallest and least massive halos, just as the first stars, by ionizing their surroundings, made it harder for the next generation to form in some environments. This is a recurring pattern in the story of the first billion years. The universe was not a linear assembly line. Every major development fed back into the conditions for the next. Stars altered the chemistry of the gas. UV radiation altered the state of the gas. Supernova explosions drove gas out of small halos. Growing black holes flooded their surroundings with radiation. Merging galaxies triggered new bursts of star formation. The result was a universe that, over the course of 1 billion years, transformed itself through a cascade of cause and effect, some of those effects reinforcing the original process, some suppressing it, some redirecting it entirely. The mathematics of that cascade, tracked through cosmological simulations involving billions of particles across billions of years of simulated time, produces large-scale structure that broadly matches what we observe: a cosmic web of filaments and voids, galaxy clusters at the intersections, large elliptical galaxies near the centers, spiral galaxies at the edges, smaller dwarf galaxies scattered throughout. But the match between simulation and observation is not perfect. It is good enough to confirm the broad picture, specific enough in its discrepancies to show where the physics is incomplete. The largest discrepancy, the one that has attracted the most attention since Webb began operating, is not about the Webb itself, but about what assembled within it, and how early. The galaxy counts at very high redshift, the masses of the earliest detected black holes, the rate at which stars were forming in the universe's first few 100 million years. All of them push harder on the models than expected. Understanding why requires going deeper than the broad outline of recombination and reionization and dark matter scaffolding into the specific physics of what the first stars actually were and what happened when they died. That is where the investigation has to go next. Because the first stars were not a beginning, they were a trigger. And what they triggered, in the chemistry of the early universe, set the terms for every generation of stars and galaxies and black holes that followed them. The first stars left no fossils. Not in the way that Earth's ancient past is recorded in layers of sediment, or even in the way that old stars leave behind white dwarfs and neutron stars we can still observe today. The very first generation of stars, the ones that formed from gas containing nothing but hydrogen, helium, and trace lithium, may have died so completely that their individual remnants are effectively undetectable with current technology. What they left behind was not matter we can point to. What they left behind was chemistry. And chemistry, it turns out, is everything. To understand what the first stars actually were, start with a constraint. A cloud of gas collapsing under gravity does not automatically become a star of any particular mass. The mass it reaches depends on a competition between two processes: gravity pulling inward and pressure, including radiation pressure and thermal pressure, pushing outward. The cloud contracts until it becomes dense and hot enough to ignite nuclear fusion, at which point the outward pressure of fusion energy balances gravity and a stable star is born. The mass at which that balance occurs depends heavily on how efficiently the gas can cool. Cooling matters because a hotter gas has higher pressure, which resists further compression. If the collapsing cloud can radiate heat away efficiently, it can compress further before pressure halts the collapse. The more efficiently a cloud cools, the more it can fragment, breaking into smaller pieces, each forming a separate, less massive star. In today's universe, star-forming molecular clouds are laced with carbon monoxide, water ice, silicate dust, and dozens of other molecular species that radiate at specific wavelengths. This chemical richness makes modern star-forming gas an efficient radiator. Modern stellar nurseries fragment readily and produce a distribution of star masses. Most stars are relatively small, some are large, very few reach extreme masses. The gas in the early universe had none of that. Pure hydrogen and helium, with a small fraction of molecular hydrogen as the only meaningful coolant. Molecular hydrogen is far less efficient at radiating heat than the molecular species available in later eras. The collapsing clouds cooled slowly, fragmented less, and the pieces that did form were consequently larger. How large is uncertain. Theoretical models have suggested masses ranging from tens to potentially thousands of solar masses for individual population 3 stars. The honest answer is that we have never directly observed a population 3 star. They formed too early and died too fast, and the models carry real uncertainties about the detailed gas physics in the early universe. What the models consistently agree on is this: population 3 stars were almost certainly more massive on average than stars forming today, and the most massive among them would have been extraordinary objects. A star of several hundred solar masses burns with a luminosity that makes the sun look dim by comparison, not modestly brighter, but millions of times brighter. It floods its surroundings with ultraviolet radiation intense enough to ionize hydrogen out to enormous distances, creating a sphere of ionized gas around it that may have been among the first individual bubbles that would eventually merge into the reionized universe. It also burns through its hydrogen fuel at a rate proportional to something like the cube or fourth power of its mass. A star 10 times more massive than the Sun burns roughly 1,000 times more luminously. The largest population 3 stars may have lived for only 1 million or 2 million years, a duration so short that, set against the timeline of the universe, They were essentially a flash. When they died, what happened depended critically on their mass. Stars in the range of roughly 25 to 140 solar masses, by current models, end in core collapse supernovae, the same general class of explosion that creates the supernova remnants we observe in our galaxy today. The core collapses to a neutron star or black hole. The outer layers are expelled in a shock wave, seeding the surrounding gas with the heavy elements synthesized during the star's life. But stars above roughly 140 solar masses, and below perhaps 260 solar masses, may end differently. As these stars exhaust their fuel and begin to cool, the cores become hot and dense enough that gamma-ray photons, the high-energy light produced by the nuclear furnace, begin spontaneously producing pairs of electrons and their antimatter counterparts, positrons. This pair production absorbs energy that was previously helping to support the star against gravity. The core destabilizes, begins to collapse rapidly, and triggers a thermonuclear explosion so energetic that it completely disrupts the star, leaving no compact remnant behind. This is a pair instability supernova. The entire star is converted, in a matter of seconds, into an expanding cloud of synthesized elements. No black hole, no neutron star, just chemistry, released explosively into the surrounding gas. The energy released is staggering. Some pair instability supernovae may have been 10 to 100 times more energetic than ordinary core collapse supernovae. The heavy elements dispersed are not ejected in narrow jets, but spread across enormous volumes of space. And those elements, primarily oxygen, silicon, sulfur, calcium, and iron, depending on the star's mass, represent the very first heavy elements to enter the intergalactic medium. For the first time in cosmic history, the gas between the forming protogalaxies contained something other than hydrogen and helium. The significance of that moment is difficult to overstate, even though no one was there to observe it. Chemistry unlocks cooling. This is the most important consequence of the first stellar deaths, and it ripples forward through every subsequent generation of stars and galaxies. Heavier elements, even in tiny amounts, dramatically improve the cooling efficiency of collapsing gas clouds. A gas cloud enriched with even 1/10,000th of the metal content of the Sun, a quantity so small it would be considered essentially pristine by modern standards, cools far more efficiently than pure hydrogen and helium. More efficient cooling means more fragmentation. More fragmentation means smaller stars. Smaller stars burn slower, live longer, and when they die, leave behind compact remnants, neutron stars and black holes, rather than vanishing entirely. The generation of stars that formed from metal-enriched gas, population 2 stars, was therefore qualitatively different from the population 3 generation that preceded it. Not just different in composition, but different in the distribution of masses, different in lifetime, different in the nature of their deaths. Population 2 stars are observable. Our galaxy contains them. Some of the oldest stars in the Milky Way, found in globular clusters and in the galactic halo, are population 2 stars that formed within the first few billion years of cosmic history. By studying their chemical compositions, the specific ratios of different elements in their atmospheres, astronomers can read a record of the supernovae that enriched the gas from which they formed. That record tells a story of progressive enrichment. The most ancient population 2 stars show chemical signatures consistent with enrichment by a small number of very massive supernovae. the kind of yields expected from population 3 stellar deaths. Slightly younger stars show enrichment from a broader mix of sources. Each generation of stellar deaths changed the raw material available to the next. The universe was manufacturing its own chemistry, one stellar generation at a time, and each generation operated under conditions set by the one that came before. But there is another product of massive stellar death that complicates this picture considerably. Black holes. When a massive population 3 star collapses without triggering a pair instability supernova, that is, when its mass falls in the range that produces a conventional core collapse, the remnant can be a black hole. And not just any black hole, but potentially a black hole of several tens or even hundreds of solar masses, called a massive stellar remnant, or, in some formation scenarios, a direct collapse black hole. These objects are the starting point for one of the most contested problems in modern cosmology: the origin of supermassive black holes. By the time the universe was 700 million years old, observations reveal quasars, galaxies whose central black holes are accreting material at such rates that they outshine the combined light of every star in their host galaxy. Some of those black holes have masses in excess of 1 billion solar masses. The most massive quasars observed at high redshift contain black holes of several billion solar masses. The problem is not that supermassive black holes exist. We see them throughout the universe today, including at the center of our own Milky Way, where a black hole of about 4 million solar masses called Sagittarius A sits largely quiet. The problem is the timescale. A black hole grows by accreting material, pulling surrounding gas and dust inward, swallowing it, converting some fraction of its mass into radiation in the process. The maximum rate at which a black hole can accrete, set by the balance between its gravity and the outward radiation pressure of the light it produces, is called the Eddington limit. Accrete at the Eddington rate continuously, and a black hole doubles its mass in a characteristic time of roughly 45 million years. Starting from a black hole of 100 solar masses, a generous seed from a population 3 stellar death, and accreting continuously at the Eddington limit, how long does it take to reach 1 billion solar masses? The math works out to roughly 900 million years. The universe was less than 700 million years old when some of those billion solar mass black holes are observed to already exist. Continuous Eddington rate accretion from a stellar seed does not fit the available time. The numbers are close enough to be tantalizing and far enough apart to be a genuine problem. 3 broad classes of solution have been proposed, and none of them is universally accepted. The first is that black holes in the early universe accreted at rates exceeding the Eddington limit, so-called super-Eddington accretion. The Eddington limit is not a hard physical barrier. Under specific conditions, if infalling gas is dense enough and geometrically arranged in ways that reduce the effective opacity, accretion can exceed the nominal limit. Some theoretical models and some observational evidence from lower redshift objects suggest that brief episodes of super-Eddington accretion occur. Whether they were common enough in the early universe to grow billion solar mass black holes from stellar seeds in the available time remains debated. The second class of solution proposes heavier seeds. Instead of beginning with stellar remnants of tens or hundreds of solar masses, some models suggest that under specific early universe conditions, gas clouds could have collapsed directly into black holes of 10,000 to 100,000 solar masses, bypassing the stellar phase entirely. In regions of particularly intense radiation, where molecular hydrogen was destroyed before the gas could cool sufficiently to fragment into stars, the entire cloud may have collapsed into what is called a direct collapse black hole. A seed of 100,000 solar masses makes the subsequent growth to 1 billion solar masses far more achievable within the available time. The problem with the direct collapse scenario is that the conditions required seem restrictive. Specific configurations of radiation environment and gas properties that may have been rare, if they occurred at all. Observations that could confirm this mechanism, directly detecting direct collapse black holes in the early universe, are at the frontier of what current and near-future telescopes can reach. The third possibility, which is not mutually exclusive with the others, is that the timescale problem is partly mitigated by early mergers. In the hierarchical structure formation picture, dark matter halos merge frequently in the early universe. When two halos merge, their central black holes eventually merge as well, though the details of how black holes sink toward the center of a merged halo and how they finally coalesce involve physics that is far from fully understood. If black holes in the early universe experienced many mergers in rapid succession, their effective growth rate could exceed what Eddington-limited accretion alone would allow. Recent results from gravitational wave observatories, which detect the ripples in spacetime produced when massive objects spiral together and merge, have confirmed that black hole mergers occur and that they involve a range of masses. The gravitational wave background signal that may have been detected by pulsar timing arrays in 2023 is consistent with contributions from supermassive black hole mergers throughout cosmic history, though its interpretation remains under investigation. None of these solutions resolves the problem completely. Each carries its own uncertainties and observational requirements. What they collectively reveal is that the growth of the first supermassive black holes involved mechanisms we do not yet fully understand, and that those mechanisms were operating during the first billion years of cosmic history, in conditions we can observe only partially. The black holes at the centers of early galaxies were not passive. They were driving one of the most energetic processes in the universe. As a supermassive black hole accretes material, it releases energy, not just as light, but in some cases as powerful jets of plasma moving at close to the speed of light, and as intense radiation across the entire electromagnetic spectrum. This energy output can be so extreme that it affects the galaxy surrounding the black hole, heating gas, pushing it outward, suppressing star formation across the entire system. This is called AGN feedback, active galactic nucleus feedback, and it represents one of the key mechanisms through which black holes shape the galaxies they inhabited. The relationship between black holes and their host galaxies is one of the more surprising findings of the last few decades of astronomy. The mass of a supermassive black hole is tightly correlated with the mass of the central bulge of its host galaxy, not loosely correlated, but tightly, across many orders of magnitude in both quantities. Galaxies with larger bulges have more massive central black holes, and the relationship holds well enough that it cannot be coincidental. This correlation implies a deep connection between the growth of black holes and the growth of galaxies, a coevolution, with each influencing the other through feedback processes. The black hole regulates star formation by heating and expelling gas. The galaxy regulates black hole growth by controlling the supply of material falling toward the center. In the early universe, this coevolution was beginning. The first quasars were not passive objects, sitting at the centers of already formed galaxies. They were active participants in shaping those galaxies, and through their radiation, affecting the gas in neighboring halos as well. The light from an early quasar, arriving at a neighboring gas cloud, could ionize hydrogen, heat the gas, and suppress the formation of stars that might otherwise have formed. A sufficiently luminous quasar could affect star formation across distances of millions of light-years. This is another layer of feedback in the first billion years, a cosmic ecology in which the most luminous objects were reshaping the environment for everything forming around them. Step back from the black holes and the feedback and the stellar generations for a moment, and consider what the universe actually looked like during this period, not as a sequence of events, but as a physical environment. By the time the universe was a few 100 million years old, the smooth sea of gas from the Dark Ages was gone. In its place was a structured landscape. Filaments of dark matter, spanning millions of light-years, intersected at nodes where matter had concentrated most densely. Along those filaments, gas flowed, drawn toward the denser regions by gravity, cooling as it went, accumulating in the growing halos. The proto-galaxies forming at those nodes were not yet the structured spirals and ellipticals of the modern universe. They were irregular accumulations of gas, star clusters, and in some cases, already active black holes, chaotic, rapidly evolving, frequently merging with neighboring systems. Mergers in the early universe were not rare events. They were routine. The universe was denser in its early phases. Halos were smaller and more numerous, and the rate at which neighboring structures encountered each other was far higher than it is today. A proto-galaxy in the first billion years might experience multiple major mergers, interactions with objects of comparable mass, in a relatively short period. Each merger was violent. Gas was compressed, heated, driven toward the center. Star formation rates spiked. Black holes fed. The merged system was left temporarily disordered, its gas distribution disturbed, its star formation history permanently altered by the event. Over multiple mergers and billions of years, these systems would eventually settle into the more regular morphologies of modern galaxies. But in the first billion years, the universe's population of proto-galaxies was a turbulent, actively evolving collection of objects undergoing continuous transformation. Within this environment, something specific was happening to the chemistry of the cosmos that is easy to overlook against the drama of mergers and black holes, but is in some ways more consequential for what the universe would eventually become. Supernovae were enriching the intergalactic medium, not just the gas immediately surrounding each exploding star, but in some cases, the gas far beyond the boundaries of the proto-galaxy itself. The energy released in a supernova explosion can drive a shock wave through the gas of its host halo, heating it and sometimes pushing it entirely out of the gravitational well of a small halo, a process called supernova-driven outflow, or galactic wind. In the smallest halos, with the shallowest gravitational potentials, supernova feedback could be violent enough to expel a significant fraction of the gas entirely. That expelled gas, carrying the heavy elements synthesized inside the dead star, dispersed into the intergalactic medium, the space between galaxies. The intergalactic medium in the first billion years was therefore not simply neutral hydrogen slowly being reionized. It was being chemically enriched by the products of the first stellar deaths, carried outward by supernova-driven winds from the earliest star-forming systems. Observations of the intergalactic medium at high redshift, through a technique called quasar absorption spectroscopy, in which the light from a distant quasar passes through intervening gas, and the chemical fingerprints of that gas appear as absorption lines in the spectrum, show evidence of heavy elements in intergalactic space, even at very early times. Carbon, oxygen, silicon, present in low but measurable abundances in gas that lies between galaxies, far from any visible stellar source. These elements got there somehow. The most natural explanation is supernova-driven winds from early star-forming systems. The chemical enrichment of the universe was not confined to individual galaxies. It was, from very early on, a process that operated across intergalactic scales. This brings the investigation to one of the deeper puzzles embedded in the first billion years, one that has become sharper since Webb began returning data. The galaxies observed at very high redshift are, in some cases, more chemically enriched than models predict. They contain heavier elements in abundances that suggest multiple generations of stellar evolution have already occurred. They are forming stars at rates that, extrapolated backward, imply the gas was converting to stars efficiently even before the epoch at which we observe them. The models are not wildly off. The broad picture of hierarchical structure formation, dark matter scaffolding, and chemical enrichment through stellar generations is not in doubt. But the specific efficiency, how quickly the early universe converted gas into stars, how rapidly the first black holes grew, how chemically mature the earliest galaxies were, these details push on the models in ways that require explanation. One possible explanation is that our models of stellar physics in the early universe are incomplete. If population 3 stars were somehow more efficient at synthesizing and distributing heavy elements than current models suggest, perhaps due to rotation, magnetic fields, or initial mass distributions that differ from theoretical predictions, then chemical enrichment could have proceeded faster than expected. Another possibility is that the early star formation efficiency was genuinely higher than models predict, driven by conditions in the early universe that are not fully captured in current simulations. The gas in early halos was denser, less disturbed by feedback from prior stellar generations, and potentially more prone to rapid conversion into stars. A third possibility, more radical and less supported but still discussed, is that some aspect of the cosmological model itself requires revision at early times. Perhaps dark matter behaves differently on small scales than the standard model assumes, or the initial conditions of structure formation carry more power on small scales than the CMB measurements imply. These are not equivalent possibilities. The first two require relatively modest revisions to our understanding. The third would require a more fundamental rethinking. Current evidence does not demand that level of revision, but the tensions in the data are real, and they are motivating a significant amount of theoretical and observational work. There is a specific observation that brings the tension into sharp focus. In 2022 and 2023, the James Webb Space Telescope observed a set of galaxies at extremely high redshift, redshifts above 10, corresponding to a look-back time of more than 13 billion years, placing them within the first few 100 million years of cosmic history. Some of these galaxies were unexpectedly bright, not slightly brighter than predicted, but in some cases significantly brighter. Bright enough that, if their luminosity came primarily from stars, their stellar masses were higher than the models anticipated for their age. Two explanations are immediately available. Either these galaxies genuinely contain more stellar mass than expected, which would require explaining how so many stars formed so quickly from gas in the very early universe, or their luminosity is boosted by contributions from active black holes at their centers, making them appear more star-rich than they actually are. Disentangling these explanations requires detailed spectroscopic analysis. Breaking the light from these galaxies into its component wavelengths to look for signatures of stellar populations versus AGN activity. Webb is capable of this analysis, and it has been applied to some of these objects. The results suggest a complicated mixture. Some of the bright early galaxies are indeed experiencing intense star formation, and some appear to have significant contributions from active central black holes. But the contribution from AGN activity does not fully account for the excess brightness in all cases. Some early galaxies appear to contain more stars than standard models comfortably accommodate. The most conservative interpretation is that the models need refinement. Specifically, the relationship between the mass of a dark matter halo and the efficiency with which it converts its baryonic gas content into stars, a relationship called the stellar-to-halo mass relation, may have been different in the early universe than it is today. If early star formation was more efficient than the late-time calibrations of that relation suggest, the observations become more understandable without requiring changes to fundamental cosmology. What drives higher star formation efficiency in early halos is, itself, an open question. But the general direction of the revision is becoming clearer. Set the galaxies aside for a moment and return to the gas, because the gas has a story running in parallel that connects everything else. During reionization, as discussed earlier, ionizing radiation from the first stars and quasars was converting neutral hydrogen into ionized plasma. But this process was not uniform across space. Different regions were reionized at different times, depending on how many sources of ionizing radiation they contained. Dense regions, with more galaxies and more stars, were reionized earlier. Voids, the underdense regions between filaments, were reionized later. The result was a patchy reionization, an era during which ionized bubbles coexisted with neutral gas in a complex, evolving geometry. From inside an ionized bubble, the universe looked transparent. Between the bubbles, neutral hydrogen still absorbed ultraviolet light. This patchiness had observational consequences that are only now beginning to be exploited. The most dramatic is the Gunn-Peterson trough, a feature in quasar spectra where neutral hydrogen in the foreground absorbs essentially all of the light at certain wavelengths, creating a complete absorption feature in the spectrum. Quasars at sufficiently high redshift, observed through gas that was still partially neutral, show this trough. Quasars at lower redshift, observed through gas that was already fully reionized, do not. By studying where the Gunn-Peterson trough appears and disappears, which quasars show it and which do not, astronomers can constrain when reionization was complete. Current evidence suggests reionization finished by a redshift of about 6, corresponding to roughly 900 million years after the Big Bang. But what about the beginning? The transition from a fully neutral universe to the first appearance of ionized bubbles. When did it start? At a redshift of 10, 20, earlier still? This is the question that upcoming radio facilities, particularly the Square Kilometre Array and its precursors, are designed to answer directly. By mapping the distribution of neutral hydrogen through its 21-centimeter emission, these instruments could, in principle, produce three-dimensional maps of the reionization process, showing the ionized bubbles growing, merging, and eventually filling all of intergalactic space. If those observations succeed, they would transform our understanding of the first billion years from a reconstruction built from indirect evidence into something more like a direct observation. The cosmic dark ages and the epoch of reionization are the last great unmapped territories in cosmic history. Epochs we know existed, can characterize broadly, but cannot yet see directly. The deepest problem revealed by investigating the first billion years is not any specific observation that does not fit. It is something more fundamental. The first billion years set the initial conditions for everything that followed. The distribution of chemical elements, the masses and structures of the first galaxies, the masses of the first supermassive black holes, the timing and geometry of reionization, all of these were established during a period we cannot directly observe in detail with current technology. The cosmological models we use to interpret what we do observe were calibrated primarily against the properties of the present-day universe and the CMB, the very beginning and the current state. The intervening history, and especially the first billion years, is reconstructed rather than directly measured. This means the models carry uncertainties that accumulate across cosmic time, and those uncertainties are hardest to constrain precisely in the regime we care about most, the earliest epochs, when the seeds of everything were being planted. What Webb has done, and what its successors will continue to do, is push the observational frontier into that regime. Every galaxy detected at high redshift, every spectrum analyzed, every chemical abundance measured in ancient stellar populations, is a data point that constrains the reconstruction. Some of those data points fit the models. Some require the models to stretch. A few require them to revise. This is how the science works, not through a single dramatic revelation, but through the gradual accumulation of evidence that collectively shapes a clearer picture. The first billion years will not be understood through one observation or one model. It will be understood through the convergence of many observations across many wavelengths with many instruments over many years. But there is a deeper layer to this problem, one that goes beyond the technical question of which models fit which data. The universe we can observe is finite. Light takes time to travel, and the universe has been expanding, which means there is a horizon beyond which we cannot see, not because there is nothing there, but because light from those regions has not had time to reach us. That horizon is fixed by physics. No telescope, regardless of how powerful, can see beyond the particle horizon, the distance light could have traveled since the Big Bang. Everything we know about the early universe comes from within that horizon. Everything we can ever observe comes from within that horizon. The physics that operated before the cosmic microwave background was emitted, the physics of the very first seconds, minutes, and years, leaves only indirect traces in what we observe, and some of those traces are degenerate. Different physical scenarios can produce similar observational signatures. The epoch of inflation, a period of extremely rapid exponential expansion thought to have occurred in the first tiny fraction of a second after the Big Bang, is the ultimate example. Inflation is strongly supported by the properties of the CMB and by the large-scale structure of the universe. It explains, among other things, why the early universe was so remarkably uniform, why space appears flat on large scales, and why the density fluctuations that seeded all subsequent structure have the specific statistical properties we observe. But inflation is not a single, well-defined theory. It is a framework within which many specific models exist. Distinguishing between those models requires observational signatures, particularly the imprint of gravitational waves produced during inflation on the polarization of the CMB, that have not yet been definitively detected. The next generation of CMB experiments, including the Simons Observatory and CMB-S4, are designed to search for exactly these signatures. If detected, they would constrain the energy scale of inflation and help narrow down which models of the very first moments are consistent with what we observe. If not detected, if the gravitational wave signature falls below the sensitivity of even these instruments, it would rule out entire classes of inflationary models and force the question of what actually drove the early exponential expansion. The first billion years, it turns out, cannot be fully understood without understanding what happened before the first second. And what happened before the first second carries its own deep uncertainties that extend backward toward a singularity we cannot observe, a moment before which our current physics breaks down entirely. This is the point where the investigation into the first billion years stops being purely historical and becomes something stranger. The question of how the universe became what it was in its first billion years is inseparable from the question of what initial conditions it started with. And those initial conditions, in turn, depend on physics operating at energies so extreme that no particle accelerator we have built, or are likely to build, can directly probe them. The unification of quantum mechanics and general relativity, the two fundamental frameworks of modern physics, is one of the central unsolved problems in theoretical physics. Quantum mechanics governs the behavior of matter and energy at the smallest scales. General relativity governs the behavior of space-time at the largest scales and highest energies. In most situations, they do not need to be reconciled, because their domains of application are well separated. At the beginning of the universe, those domains were not separated. The universe was, in its first moments, simultaneously at the smallest scales and the highest energies imaginable. Quantum effects and gravitational effects were operating simultaneously on the same system. Without a theory of quantum gravity, a framework that successfully unifies these two pillars of physics, the very earliest moments of the universe are literally beyond the reach of our current mathematics. The equations break down at what is called the Planck time, approximately 10 to the minus 43 seconds after the Big Bang, because that is where quantum gravitational effects become so dominant that the space-time description of general relativity ceases to be valid. What happened at or before the Planck time is, in a technically precise sense, currently unknowable with existing physical theory. It is not merely that we lack the observations. We lack the mathematics to even formulate the question correctly. The investigation of the first billion years begins, in a sense, with this wall behind it, an absolute observational and theoretical boundary beyond which our investigation cannot currently reach. Everything within that first billion years exists between two walls. The Planck epoch at one end, where physics as we know it fails, and the epoch of reionization at the other end, where the neutral hydrogen fog finally cleared and the universe became fully transparent to the kinds of light we can observe across cosmological distances. Between those walls, the CMB, the Dark Ages, the first stars, the first heavy elements, the first galaxies, the first supermassive black holes, reionization itself. Each of these is understood to some degree. Each carries important uncertainties. And the uncertainties are not randomly distributed. They cluster around specific problems. The formation of the first stars. We know they existed. We know they were more massive than modern stars on average. We do not know their precise mass distribution or their individual properties. The growth of the first black holes. We know they grew to enormous masses in a short time. We have several plausible mechanisms for how. We do not know which mechanism dominated or in what combination. The history of reionization. We know approximately when it ended. We can constrain broadly when it began. We cannot yet map the detailed geometry of how it proceeded. The chemical enrichment of the intergalactic medium. We know enrichment occurred early and extensively. We do not know the precise balance of contributions from different stellar populations and different types of outflows. The properties of the earliest galaxies. We are actively discovering that some are different from what models predicted, and we are working out what that means. These are not minor uncertainties at the edges of an otherwise complete picture. They concern the foundational events of cosmic history, the processes that determined what the universe would look like for the next 12 billion years, including the formation of the Milky Way, the solar system, and everything in it. There is something quietly unsettling about this situation. We live inside a universe that we can observe in extraordinary detail. We have mapped galaxies across billions of light years. We have measured the compositions of distant stars with enough precision to reconstruct what supernovae created them. We have detected gravitational waves from black hole mergers more than 1 billion light-years away. We understand, with remarkable depth, the physical laws that govern what we see. And yet the first chapter of the story we are part of, the billion years that built the initial conditions for everything we see around us, remains partially obscured. Not because the evidence does not exist, but because it lies in regimes that our current instruments are only beginning to reach, and in physics that our current theories are only beginning to approach. The James Webb Space Telescope is extraordinary, but it cannot see through the Gunn-Peterson trough. It cannot map the neutral hydrogen fog of the epoch of reionization directly. It cannot observe the Dark Ages. It can see the aftermath, galaxies that formed during and shortly after these events. But the events themselves are accessible only indirectly. Every observation Webb makes of a high redshift galaxy is, in this sense, an act of forensic reconstruction. The galaxy exists as evidence of what happened. The task is to read that evidence carefully enough to reconstruct the process that produced it. This is not a criticism of Webb or of the scientists using it. It is a description of the nature of the problem. The early universe genuinely hides its history behind physical barriers. The opacity of neutral hydrogen, the finite speed of light, the breakdown of classical physics at the earliest moments. That cannot be wished away by building a more sensitive telescope. What can be done is to approach those barriers from multiple directions simultaneously. Optical and infrared observations from Webb probe the galaxies that formed during and after reionization. Radio observations probe the 21-centimeter signature of neutral hydrogen directly. Gravitational wave observatories probe the mergers of compact objects that began accumulating in the first billion years. CMB experiments probe the imprint of early physics on the microwave background. Computational simulations synthesize all of this into theoretical models that can be tested against the observations. No single approach is sufficient. The first billion years is a puzzle that requires every tool simultaneously. And within that puzzle, one question keeps returning. Not because it is the only important question, but because it sits at the intersection of everything else. How did the universe go from the near-perfect uniformity of the CMB to the structured complexity we see today, in just a billion years, under physical laws that we mostly understand? The answer is not fully known. The broad mechanism, density fluctuations, dark matter scaffolding, gravitational collapse, stellar generations, chemical enrichment, black hole growth, reionization, is clear. The details, the timing, the efficiencies, the feedback mechanisms and their relative importance, these are where the frontier lies. And the frontier keeps moving, because the observations keep arriving. Every new high redshift galaxy, every new quasar spectrum, every new detection of chemical enrichment in ancient gas, every gravitational wave event, every CMB polarization measurement, each narrows the space of possibilities. The reconstruction becomes more constrained. The picture becomes sharper. The uncertainties become smaller. But the most important uncertainties, the ones that bear on what happened before the first stars, on what gave the universe its initial conditions, on what physics operated at energies we cannot reproduce in any laboratory, those uncertainties have a different character. They are not narrowing as fast. In some cases, they are revealing that the questions we were asking were not quite right, that the boundaries between what we know and what we do not know are located at different places than we thought. The first billion years of everything is not just the opening chapter of cosmic history. It is a mirror. Every time we push our instruments deeper into that era and discover that reality was more complex, more surprising, or more efficient than our models predicted, we are not just learning about the early universe. We are discovering the limits of the intuitions we built, from observing a universe that is already 13 billion years into its story. The first billion years is the part of the story that explains everything that came after it, and it is, still, only partially read. What it means, not just for our models of galaxy formation or black hole growth, but for our understanding of where we came from and why anything exists, to ask the question, is what the investigation has to face next. There is a version of this story that ends with the science. The universe began in a hot, dense state. Gravity worked on small fluctuations in the density of matter. Dark matter collapsed first, providing scaffolding. Gas fell in. Stars formed. They died, scattering chemistry. New stars formed from that chemistry. Galaxies assembled through mergers. Black holes grew at their centers. Reionization cleared the hydrogen fog. The universe became the structured, chemical, light-filled cosmos we observe today. That version is largely correct. It is also incomplete. Not because it omits important physics, but because it treats the first billion years as a sequence of events that happened elsewhere, to matter that had nothing to do with the matter that eventually became us. That assumption is wrong. The carbon in every living cell on Earth was synthesized inside a star. The oxygen in every breath was forged in stellar cores and scattered by supernova explosions. The iron in the hemoglobin carrying oxygen through your blood right now was produced in the collapse of a massive star, perhaps several massive stars, before the solar system existed. The calcium in bone, the nitrogen in DNA, the silicon in rock. Each element has a specific astrophysical origin, a specific type of stellar event that produced it, a specific chapter in the history of the universe in which it first appeared. The first billion years is therefore not merely the opening chapter of cosmic history. It is the opening chapter of the only kind of chemistry that makes biology possible. Consider what it took. The Big Bang produced hydrogen, helium, and a tiny amount of lithium. That is almost the entire initial inventory of the universe's chemistry. 3 elements out of the 92 that occur naturally. Everything else required stars. But not just any stars. The lightest elements up to iron are produced in stellar fusion, the nuclear reactions that power stars throughout their lives. The elements heavier than iron, which cannot be produced by fusion because doing so would consume energy rather than release it, require different and more violent events. The explosive shock waves of supernovae, the neutron-rich environments of neutron star mergers, the extreme conditions of rapidly accreting compact objects. Gold, platinum, uranium, iodine. These elements were not made in stellar cores. They were made in violence, in the final seconds of stellar deaths, in the collisions of neutron stars, in environments so extreme that nuclei were being assembled faster than they could decay. The detection of gravitational waves from a neutron star merger in 2017, accompanied by light across the electromagnetic spectrum, confirmed directly that these events produce heavy elements. The kilonova explosion that followed the merger showed spectroscopic signatures of freshly synthesized gold, platinum, and other heavy elements. Every atom heavier than iron in your body, on this planet, in this solar system, passed through at least one catastrophic astrophysical event before it arrived here. Some of it passed through several. This is not poetry. It is nuclear astrophysics. The origin of each element in the periodic table is mapped to specific stellar processes with enough precision that the field has a name, stellar nucleosynthesis, and enough evidence that the broad picture is not seriously disputed. What it means is that the story of the first billion years and the story of chemistry on Earth are the same story. The population 3 stars that exploded in pair instability supernovae hundreds of millions of years before the solar system formed. The violence of their deaths is recorded in the chemical composition of the oldest stars in our galaxy, and in trace abundances of elements in the solar system's oldest material. The universe's first billion years wrote the first lines of a chemical record that every subsequent generation of stars, planets, and living systems has been reading ever since. Now hold that thought and consider scale. The observable universe contains somewhere in the range of 2 trillion galaxies, a number revised upward from earlier estimates when a 2016 analysis of deep field images suggested that previous surveys had missed enormous numbers of faint, small galaxies at high redshift. Each of those galaxies contains, on average, hundreds of billions of stars. The total number of stars in the observable universe is estimated at roughly 10 to the power of 24, a 1 followed by 24 zeros. That number is larger than the number of grains of sand on all of Earth's beaches. It is larger, in fact, than the estimated number of grains of sand on a planet made entirely of sand, the size of Earth. Numbers of this magnitude resist intuition. They are too large to feel. But here is what gives that number meaning in the context of this investigation. Every one of those stars, without exception, owes its existence to processes that began in the first billion years of cosmic history. The chemical conditions that made star formation possible in later eras, the presence of heavier elements, the cooling mechanisms they enable, the dust grains that help gas radiate heat, all of those were established by the first stellar generations. The large-scale structure of dark matter, within which every subsequent galaxy assembled, took its essential shape during the first billion years. The 2 trillion galaxies we observe today are the downstream consequence of events that occurred in the first 8% of cosmic history. The relationship between those early events and the present universe raises a question that is scientifically precise, even though it sounds philosophical. How contingent was it? In other words, how much did the specific details of the first billion years matter for what the universe became? This is not an idle question. Cosmological simulations give us a way to probe it, at least partially. When researchers run multiple simulations with slightly different initial conditions, varying the amplitude of density fluctuations, the properties of dark matter, the efficiency of stellar feedback, they find that the large-scale structure of the universe is relatively robust. The cosmic web of filaments and voids, the general distribution of galaxy masses, the overall star formation history, these broad features emerge across a range of initial conditions. But the details are not robust. Small changes in the efficiency of supernova feedback, for example, produce significant changes in the population of dwarf galaxies. Small changes in the assumed properties of dark matter alter the density profiles of galactic halos in ways that affect the sizes of galaxies. The mass distribution of the first stellar generation, the initial mass function of population 3 stars, affects the chemical enrichment history, which affects subsequent star formation, which propagates forward through cosmic time. The universe we observe today is one realization of an initial condition set in the first billion years. Whether a slightly different early universe would have produced, 12 billion years later, something broadly similar, or something dramatically different, that depends on which details you change and by how much. What the simulations suggest is that some features of the present universe are robust across a wide range of early conditions, while others are sensitive to details that we cannot currently constrain with high precision. The existence of galaxies, of stars, of heavy elements, these seem robust. The specific properties of any given galaxy, its size, its star formation history, its chemical evolution, are more sensitive to the particular path its assembly took. The Milky Way's specific history is one path among many that were available given the initial conditions of the first billion years. That it produced among its hundreds of billions of stars a sun of a particular mass, with a planetary system of a particular architecture, on which chemistry eventually became biology. That specific outcome is not demanded by the broad parameters of early cosmic history. It is one specific realization. Among how many possible realizations, we genuinely do not know. This is where the investigation stops feeling like astrophysics and starts feeling like something harder to name. The observable universe is bounded by the particle horizon, the distance light has had time to travel since the Big Bang. Beyond that horizon, space continues. By most cosmological models, it continues for a very long way, possibly indefinitely, if the universe is infinite. If the universe is infinite in spatial extent, then every configuration of matter that is physically possible occurs somewhere, because an infinite volume with a finite number of possible configurations of matter on any given scale must repeat. Somewhere, by this argument, there is a region that looks exactly like the observable universe. Somewhere, more distantly, there is a region identical to our observable universe, down to the position of every atom. This is not mysticism. It is a straightforward consequence of infinite volume and finite physical possibilities at any given scale. The physicist Max Tegmark has called these regions Level 1 multiverses, not other dimensions or other physical laws, simply other regions of an infinite universe, separated by such vast distances that they lie beyond each other's particle horizons. Whether the universe is actually infinite in extent is not known. Cosmological observations constrain the curvature of space on the scales we can observe, and the data is consistent with a flat universe, which could be infinite. But consistent with flat does not prove infinite, and the question may be fundamentally unanswerable with any observation made from within a finite horizon. What this means practically is that the question, how contingent was our specific cosmic history, may not have an answer accessible from within our observable patch. If the universe is large enough, and especially if inflation produced a vast or infinite volume, then the full range of initial conditions and their consequences is being explored somewhere. Our specific first billion years, with its specific population 3 stars, and its specific reionization history, and its specific early black holes, produced our specific universe. Other initial conditions, or the same initial conditions with different random fluctuations, may have produced, or may elsewhere be producing, other universes with different properties. This is a legitimate scientific framework, the inflationary multiverse, with real predictive content and real observational constraints. It is also a framework that, if correct, fundamentally changes what it means to explain why the universe is the way it is. But there is a version of this question that does not require infinite universes or speculation about what lies beyond the horizon. Within the observable universe, within the history of the first billion years, there is already something deeply strange about the relationship between the initial conditions and the outcome. The density fluctuations in the early universe, the tiny variations in matter density imprinted at recombination and visible in the CMB, have a specific statistical character. They are scale invariant, or close to it. Fluctuations of the same amplitude exist across a wide range of spatial scales. This particular statistical signature is not arbitrary. It is predicted by inflationary models, and it is the statistical character that, fed through gravitational collapse over 13 billion years, produces a universe whose large-scale structure matches what we observe. A different statistical character, fluctuations with more power on small scales, or less power on large scales, or strongly non-Gaussian statistics, would have produced a different large-scale structure. Whether that different structure would have eventually produced stars and chemistry and biology is an open question. Some variations might have, others clearly would not. The universe appears to have been initialized with conditions that were, at minimum, compatible with the eventual emergence of chemical complexity. How narrowly compatible, whether the conditions were fine-tuned to that outcome or whether a wide range of initial conditions would have worked, is a question that physicists disagree about genuinely and substantively. This is the anthropic territory of cosmology, and it is uncomfortable precisely because it sits at the boundary between physics and philosophy, in a way that cannot be neatly resolved by observation. There is, however, a more concrete version of the strangeness that does not require going to the edges of physical theory. Consider the timeline of the first billion years from the perspective of what it produced. The first stars formed and died within the first few 100 million years, seeding the universe with heavy elements for the first time. The second generation of stars formed from that enriched gas, burned, and died, enriching the gas further. By the time the universe was 1 billion years old, the intergalactic medium already contained measurable amounts of carbon and oxygen and silicon, elements that, on Earth, are the backbone of biochemistry and geology. The solar system formed 4.6 billion years ago, roughly 9 billion years after the Big Bang. By the time the gas cloud that would become the Sun and its planets began to collapse, it had been chemically enriched by at least several generations of stellar deaths. The heavy elements in that cloud, including all the carbon, oxygen, nitrogen, phosphorus, and other biologically important elements, were inherited from supernovae and stellar winds and neutron star mergers that had been occurring throughout cosmic history, including in those first billion years. The universe spent its first billion years building the chemistry it would need for everything that came after. It did not do this purposefully. The language of purpose is not appropriate here. It did it because the physics of nuclear fusion in stellar cores, followed by the physics of stellar death, followed by the physics of chemical enrichment, followed by the physics of subsequent star formation, produced this outcome inevitably given the initial conditions. But inevitably, given the initial conditions, is not the same as inevitably full stop. The initial conditions were what they were, and we are here, made of the products of stellar nucleosynthesis, able to look back across 13 billion years and trace the chain of events that produced the atoms we are made of. That chain began in the first billion years. It began with stars we have never observed and cannot directly detect, burning in protogalaxies whose structures we are only now beginning to probe with our best instruments. It began with supernovae that left no visible remnants, only chemistry, scattered across intergalactic space, that eventually found its way into molecular clouds, into protostellar disks, into planets, into oceans, into cells. The observation that we are made of stellar material is not new. It has been part of popular science communication for decades. What tends to get lost in the casual retelling is the precision and depth of the claim. It is not merely that atoms in our bodies were once in stars. It is that the specific distribution of elements in our bodies, the ratio of carbon to nitrogen to oxygen to phosphorus, reflects the specific nuclear astrophysics of the stellar populations that enriched the gas from which the solar system formed. The balance of elements in living systems is not arbitrary. It reflects, in part, the availability of those elements in the solar environment at the time of Earth's formation. And that availability reflects the specific history of chemical enrichment, including the contributions from the first billion years of stellar nucleosynthesis. Carbon-based biochemistry is not the only possible chemistry, but it is the chemistry that the universe produced in abundance, because carbon is synthesized efficiently in stellar cores through the triple alpha process, the fusion of 3 helium nuclei, and scattered widely by stellar winds and supernova explosions. The universe became, over its first few billion years, saturated with carbon in a way that reflects the specific nuclear physics of the stars that lived and died during that period. Whether a universe with different nuclear physics, different values of the fundamental constants governing the strength of the strong force, or the fine structure constant, could have produced different but equally rich chemistry is a question that physicists have investigated seriously. Small changes in some constants would have prevented stable carbon from forming efficiently. Other changes would have altered stellar lifetimes in ways that might have prevented the enrichment cycle from proceeding. The sensitivity of carbon production to the values of certain nuclear resonances, specifically the Hoyle state of carbon-12, which must fall at just the right energy level for the triple alpha process to proceed efficiently, was noted by the astrophysicist Fred Hoyle in the 1950s, and has been discussed ever since as one of the more striking examples of apparent fine-tuning in nuclear physics. Whether this reflects a genuine constraint on the possible range of life-permitting universes, or whether it reflects our own limited imagination about what other forms of complexity could arise under different physical laws, remains an open and contested question. What is not contested is this: the first billion years determined the chemical environment of every subsequent cosmic era. The stars that formed after the first billion years formed in gas that had already been enriched by the stars that formed within it. The galaxies that assembled after the first billion years assembled within dark matter structures that had already taken their essential shape. The black holes that grew after the first billion years grew from seeds planted during it. The first billion years was not prologue, it was foundation. And the foundation was built during a period we cannot yet fully observe. From initial conditions, we cannot yet fully constrain. Through processes we understand in broad outline, but not in all the details that mattered. This is the position the investigation has reached. Not paralysis. The science is advancing. The observations are accumulating. The models are being refined. But a specific kind of intellectual humility that comes from recognizing that the most important chapter of the story we are part of is also the chapter we can read least completely. The matter we are made of passed through the first billion years of everything. It was there when the first stars ignited. It was scattered by the first supernovae. It drifted through the intergalactic medium during the Dark Ages. It was swept into new clouds by the turbulence of early galactic mergers. It was forged and scattered again, multiple times, through multiple stellar generations, before it found its way into a molecular cloud that would become the solar system. That journey, from the first stars to here, spans 13 billion years, and involves processes operating from the quantum scale to the scale of galaxy clusters. We are not observers of the first billion years. We are, in a very specific physical sense, its product. And what we have built, instruments sensitive enough to see galaxies forming within the first few 100 million years of cosmic history, mathematical frameworks powerful enough to simulate the formation of structure across billions of years, a theoretical understanding deep enough to recognize where it breaks down, is perhaps the most remarkable downstream consequence of those first stellar deaths. Not because it gives us the answers, because it gives us the questions. The first billion years produced chemistry. Chemistry produced complexity. Complexity, in one corner of one galaxy among 2 trillion, eventually produced the capacity to ask what happened in the first billion years. That loop, from the early universe to the mind contemplating the early universe, has a quality that no physical theory yet adequately describes. It is where the science ends and something else begins. And it is where the investigation must now go. Return to the beginning. Not the beginning of this investigation, the beginning of everything. A universe so hot and dense that space itself was a furnace. No atoms, no molecules, no structure of any kind. Just energy and fundamental particles in a state so extreme that the four forces governing all physical interactions may have been unified into a single phenomenon, a single underlying dynamic, that, as the universe cooled and expanded, broke apart into the distinct forces we recognize today. We began this investigation by noting that something about the first billion years does not quite fit, that the universe assembled structure, chemistry, and complexity faster than our models comfortably explain, that galaxies appeared earlier and more massive than expected, that black holes grew to extraordinary sizes in seemingly insufficient time. But now, having followed the chain of events from the clearing of the primordial plasma through the Dark Ages, through the first stellar ignitions, through chemical enrichment and reionization, and the emergence of structured galaxies, having traced that chain all the way to the question of what it means that the matter in living systems is the direct product of stellar nucleosynthesis, the original puzzle looks different. It is not just that the universe assembled things quickly. It is that the universe assembled the right things. It is that the chain of physical processes that ran through the first billion years produced not merely structure, but the specific kind of structure, chemically rich, hierarchically organized, energetically active, from which everything recognizable to us eventually descended. That is the deeper puzzle, and it does not resolve cleanly. Here is what the investigation has established. The early universe was almost perfectly uniform. The density fluctuations imprinted at recombination were 1 part in 100,000, extraordinarily small by any ordinary standard. Those fluctuations were not random in the everyday sense. They had a specific statistical character, scale invariant and Gaussian, consistent with being produced by quantum fluctuations during an inflationary epoch, and then stretched to cosmic scales by the expansion of space. Quantum fluctuations, in the first fractions of a second, stretched across the observable universe. The large-scale structure of the cosmos, the 2 trillion galaxies, the cosmic web of filaments and voids spanning hundreds of millions of light-years, the clusters of thousands of galaxies at the nodes of that web. All of it traces back to quantum-scale variations in the density of the early universe. This is not a metaphor. It is the actual physical mechanism, supported by the precise agreement between the statistical properties of the CMB and the statistical properties of the large-scale structure of the universe today. The pattern of galaxies on the largest scales is the pattern of quantum fluctuations, magnified and evolved by gravity across 13 billion years. The universe we live in, including everything in it, is the macroscopic consequence of microscopic uncertainty. This is where the 2 great frameworks of modern physics, which spend most of their existence in separate domains, touch each other in a way that has physical consequences we can observe. Quantum mechanics governs the behavior of matter and energy at the smallest scales. Its central feature is not simply that small things are hard to measure. Its central feature is that, before measurement, many physical quantities do not have definite values. A quantum system exists in a superposition of possibilities, and which possibility is realized upon interaction with the environment involves an irreducible element of indeterminacy. General relativity governs the behavior of space-time, the geometry of the universe on large scales. It describes how mass and energy curve space, how that curvature determines the motion of everything within it, how the universe expands and what drives that expansion. These two frameworks have resisted unification for a century. At the energies and scales of everyday physics, and even at the energies of current particle accelerators, they operate in separate regimes, and their incompatibility does not matter practically. But at the beginning of the universe, at the Planck epoch, when quantum gravitational effects dominated, they cannot be kept separate. What inflation does, in the standard picture, is take the quantum indeterminacy that is intrinsic to the early universe and translate it into classical density variations that gravity can then act upon. The quantum fluctuations become the seeds of the cosmic web. The irreducible uncertainty of the quantum world becomes the pattern from which the macroscopic world is built. If this picture is correct, and the evidence supporting it, while not conclusive, is substantial, then the existence of galaxies, of stars, of heavy elements, of planets, of biology, of the capacity to ask questions about the early universe, all ultimately traces to quantum indeterminacy in the first instant of cosmic history. The universe is structured the way it is because of what quantum mechanics did in its first moments. And quantum mechanics, at its foundation, involves a kind of fundamental openness, a universe that was not predetermined in every detail, but was realized through a process in which many outcomes were possible. This is the realization that the entire investigation has been building toward. Not because it answers every question, but because it reframes all of them. Let it land. The atoms in your body were forged in stellar cores and scattered by stellar deaths. That much was established in Section 4. But the stars that made them formed in specific locations, in specific halos, at specific times, locations and times that were determined by the specific pattern of density fluctuations in the early universe. Those density fluctuations were produced by quantum processes in the first fraction of a second, which means the specific path that matter took through the first billion years, the specific halos that formed first, the specific locations where the first stars ignited, the specific supernovae that scattered chemistry into specific regions of the intergalactic medium, all of that was not predetermined at the moment of the Big Bang. It was shaped, in part, by quantum processes whose outcomes involved genuine indeterminacy. The matter that became you did not have a predetermined trajectory from the first moment of the universe. Its path was shaped, in the very first instant, by processes that quantum mechanics describes as inherently non-deterministic. And then, over 13 billion years of gravitational collapse, stellar evolution, chemical enrichment, planetary formation, and biological evolution, that matter arrived here, in this configuration, capable of reconstructing the sequence of events that shaped its own path. The loop closes, and closing it reveals something unsettling. We have been treating the first billion years as the object of investigation, the thing being studied. But there is a sense in which the first billion years is also doing the investigating. The matter engaged in this act of understanding, the neurons firing, the concepts forming, the mathematics being applied, is made of atoms that passed through the first billion years. The instruments we built to observe the early universe are made of metals that were synthesized in stellar interiors and scattered by supernova explosions. The mathematical frameworks we use to model the early universe were developed by minds that are themselves late products of the cosmic chemical evolution that the early universe initiated. There is no view from outside this system. Every perspective on the early universe is a perspective from within it, from a vantage point that the early universe itself produced. This is not an argument for any particular philosophical conclusion. It is a structural feature of the situation that has precise scientific content. It means that our ability to understand the early universe is bounded not just by the limits of our instruments, but by the limits of what a mind produced by 13 billion years of cosmic evolution can comprehend. The physics of the early universe operated at energy scales and spatial scales and temporal scales that have no analog in any experience that shaped human intuition. The first microsecond of cosmic history involved processes so different from anything in our sensory or evolutionary experience that our intuitions are not merely inadequate guides to what happened. They are actively misleading. The mathematics works. The intuitions do not. And yet the mathematics was developed by human minds. The observations are interpreted by human reasoning. The models are constructed from concepts that, however abstract, are ultimately grounded in a kind of thinking that evolved for entirely different purposes. The universe, in its first moments, was doing things that no human concept was built to describe. And we are using human concepts to describe them. This is not a reason for despair or for skepticism about the scientific enterprise. It is, in fact, the opposite. The extraordinary thing is not that our understanding is incomplete. The extraordinary thing is how far it reaches. We cannot directly observe the first stars, but we can read their chemical signatures in the oldest stars in our galaxy. We cannot see the epoch of reionization, but we can map its end through the Gunn-Peterson trough in quasar spectra. We cannot probe the Planck epoch, but we can constrain the physics of inflation through the statistical properties of the CMB. We cannot watch a population 3 star explode, but we can detect gravitational waves from the mergers of the black holes that stellar deaths may have left behind. Every one of these is a form of inference, reasoning from effects back to causes, from the observable present to the unobservable past. And that inference is not guesswork. It is constrained by physical law, tested against independent observations, refined by the accumulation of evidence from multiple directions simultaneously. What this means is that the investigation of the first billion years is, in a deep sense, an act of self-reconstruction. The universe, through the particular corner of itself that developed scientific reasoning, is attempting to reconstruct its own history, to trace the chain of causes that produced, among other things, the capacity to trace chains of causes. That is not guaranteed to succeed completely. There are physical limits, the particle horizon, the opacity of the neutral hydrogen era, the breakdown of classical physics at the Planck epoch, that may permanently limit how far back the reconstruction can go. Some aspects of the first billion years may be permanently inaccessible. But the limits of what is knowable are themselves physically meaningful. They are not arbitrary. They reflect the structure of the universe, the finite speed of light, the quantum nature of matter, the behavior of space-time at extreme energies. Even the boundaries of our knowledge are telling us something about the early universe. Return now to the central tension that opened this investigation. The universe was almost perfectly uniform at 380,000 years. It was substantially structured by 1 billion years. The gap between those two states, bridged by dark matter scaffolding and stellar evolution and chemical enrichment and black hole growth and reionization, is the most consequential billion years in cosmic history. And the tension in the data, the galaxies that are more massive than expected, the black holes that grew faster than models comfortably accommodate, the chemical enrichment that proceeded further and faster than simulations predicted. That tension is not a crisis for the standard cosmological model. It is a signal. It is the universe telling us that our reconstruction of its first billion years, good as it is missing something. Not the broad strokes. Those are well established. Something in the details. Something in the efficiency of early star formation, or the mechanism of early black hole growth, or the physics of feedback in the first galaxies, or perhaps something more fundamental about the initial conditions themselves. The James Webb Space Telescope will continue operating for years. Radio facilities designed to map the 21-centimeter hydrogen signal are being built. Gravitational wave observatories are being upgraded and new ones are planned. CMB experiments capable of detecting the inflationary gravitational wave signal are in development. Computational simulations are becoming more sophisticated, incorporating more realistic physics on smaller scales. The reconstruction will continue. The uncertainties will narrow, in most areas. Some surprises will resolve into revisions of detail. Others may turn out to require more significant revision. And the possibility remains. It is a genuine scientific possibility, not a dramatic flourish, that somewhere in those narrowing uncertainties lies a discovery that significantly changes how we understand the first billion years. Not a revolution that overturns everything, but a revelation that reframes something important. That is what the history of cosmology looks like. Not steady linear progress toward complete understanding, but a sequence of frameworks refined by evidence, occasionally reorganized by discoveries that reveal an assumption was wrong, or a parameter was misunderstood, or a mechanism was missing. The discovery that the universe's expansion is accelerating, which led to the concept of dark energy, was not predicted. The discovery that the universe is geometrically flat on large scales required a period of significant theoretical adjustment. The discovery that black holes were common at the centers of galaxies, rather than rare curiosities, changed our understanding of galactic evolution fundamentally. The investigation of the first billion years is still young enough that discoveries of comparable significance remain possible, perhaps probable. Here is what the journey has revealed. The first billion years of everything was not an overture to the real story. It was the story, the period in which the universe built the conditions for all of its subsequent history, including the conditions that would eventually produce the capacity to investigate what happened. It was a period defined by processes operating at every scale simultaneously, quantum fluctuations becoming classical density variations, dark matter halos assembling from the bottom up, gas cooling through molecular emission, the first stars igniting and dying in explosions that scattered chemistry across intergalactic space, new stars forming from that enriched gas, black holes growing through accretion and mergers, ionizing radiation transforming the state of the intergalactic medium, galaxy mergers driving new bursts of star formation, feedback from black holes reshaping the gas that would form future stars. These processes were not independent, they were coupled. Each affected the conditions for the others. The result was a universe that transformed itself through a cascade of cause and effect, so tightly interwoven that it cannot be understood by studying any single thread in isolation. And at the base of all of it, at the foundation of the density fluctuations that seeded the entire structure, at the origin of the specific pattern that gravity would spend 13 billion years amplifying, quantum mechanics. The universe is not a clockwork. It never was. Its structure emerged from an initial condition that contained genuine indeterminacy, shaped by processes whose outcomes were not predetermined, evolved by gravity and nuclear physics into the specific configuration we find ourselves in. That specific configuration includes planets, oceans, chemistry that self-replicates, biology that develops nervous systems complex enough to model the universe that produced them. None of that was written into the Big Bang. All of it followed from it, through a chain of events that the first billion years set in motion. There is a question that this realization opens, not closes. If the structure of the universe traces to quantum fluctuations in the first instant, if the specific pattern of density variations that determined where every galaxy would form was shaped by processes involving genuine indeterminacy, then in what sense can we say that the universe had to become what it became? Physics gives us the laws. The laws tell us how systems evolve given initial conditions. But the initial conditions of the observable universe, including the specific realization of those quantum fluctuations, are not derivable from the laws alone. They are, in a precise technical sense, contingent. The universe could have been initialized differently. In inflation, in fact, it almost certainly was. Different regions of a vast inflated volume would have different realizations of those fluctuations, producing regions with different large-scale structures, different galaxy populations, different chemical histories. Whether any of those other regions are physically real, and whether they contain their own versions of this question being asked, is something current physics cannot answer. What current physics can say is this: the specific first billion years that produced our specific universe was not inevitable. It was one realization among a range of possibilities that quantum mechanics and inflation together made available. We exist in the specific realization we exist in. We are asking about it because it produced us, and we cannot step outside it to see what the alternatives looked like. The investigation of the first billion years, pursued far enough, arrives at this boundary, the edge of what physical theory can currently tell us, the edge of what observation can currently reach, and the edge of what a mind shaped by the specific history of this specific universe can fully comprehend. Beyond that boundary lies not silence, but the next set of questions, questions whose precise formulation depends on discoveries that have not yet been made. That is where the universe has brought us. 13 billion years from the first quantum fluctuations to this moment of reflection. A billion years of construction, and 12 billion more of consequence, leading to a corner of one galaxy where matter has organized itself into something capable of reconstructing the story of its own origin, and discovering, in the reconstruction, that the origin contains irreducible uncertainty all the way down. The first billion years made everything, including the wondering. We began with a number that did not make sense. A universe that, within its first billion years, assembled galaxies more massive than expected, grew black holes faster than the physics seemed to allow, distributed chemistry across intergalactic space, before the models predicted it should have been possible. A universe that moved from featureless plasma to structured complexity, with a speed that still strains our best explanations. That original tension has not been resolved. What has changed is what we understand the tension to mean. It is not a flaw in the data. It is not a measurement error waiting to be corrected. It is a signal, from the most consequential period in cosmic history, that our reconstruction of what happened is good but incomplete. That the first billion years, for all the evidence we have gathered and all the models we have refined, is still partially hidden from us, behind the opacity of neutral hydrogen, behind the limits of our instruments, behind the boundary where our mathematics breaks down and the universe's earliest moments become genuinely inaccessible to current physical theory. What we have learned is not that the mystery is smaller than it appeared. We have learned that it is structured differently than it appeared. The question is no longer simply how the universe assembled things so quickly. The question is what the first billion years reveals about the nature of the universe itself, about how a cosmos that began in near-perfect uniformity, shaped by quantum indeterminacy in its first instance, could produce, through an interlocked cascade of gravitational collapse and stellar death and chemical enrichment, the conditions for everything recognizable to us, including the recognition itself. The science will continue. The James Webb Space Telescope will push deeper into the epoch of reionization. Facilities designed to map the 21-centimeter hydrogen signal will attempt to image the dark ages directly, to show us the neutral hydrogen fog and the ionized bubbles growing within it in real time, as close to real time as light travel delay allows. Gravitational wave observatories will accumulate a census of compact object mergers that traces back to the first stellar deaths. CMB experiments will search for the polarization signature of inflationary gravitational waves, a signal that, if detected, would constrain the energy scale of the universe's first fraction of a second. Each of these observations will narrow specific uncertainties. Some will confirm what the models predict. Some, almost certainly, will not. The history of cosmology offers a consistent lesson. The universe is more specific than the models, and the discrepancies between what we expect and what we find are where the most important new understanding tends to emerge. The accelerating expansion that revealed dark energy, the galaxy rotation curves that established dark matter, the CMB uniformity that required inflation. Each came from a measurement that did not fit, from a number that seemed wrong, from a tension that turned out to be telling the truth. The tensions in the data about the first billion years are real. They are being taken seriously. And they are younger, as tensions go, than any of the discoveries that resolved earlier ones. What they will eventually reveal is not yet clear. That uncertainty is not a weakness of the science. It is the science working exactly as it should, building toward an understanding that is always more accurate than the last version, and always less complete than the next. There is one question that this investigation has not answered, and cannot answer, because no current observation or theory can answer it. Why did the quantum fluctuations of the early universe have the specific character they had? The scale-invariant, Gaussian spectrum of density fluctuations that seeded all subsequent structure is predicted by broad classes of inflationary models. Inflation explains why fluctuations of that character exist. But inflation itself requires an explanation, a mechanism that drove the exponential expansion, an energy source that sustained it, a reason it ended when it did, and not earlier or later. The theories of inflation involve fields and energy scales that are, for now, beyond direct experimental access. The specific model of inflation that produced our universe, among the many inflationary models that are consistent with current CMB observations, is not known. It may not be knowable with observations made from within the universe inflation produced. And behind inflation lies the deeper question of initial conditions. Why the universe began in a state from which inflation could proceed. Why there is something rather than nothing. Why the physical laws have the form they have, rather than some other form. These are not questions that science currently has the tools to answer. They may be questions that science will never have the tools to answer, because they concern the origin of the framework within which science operates. That boundary is real. It is not a failure. It is the honest edge of what the investigation can reach. The first billion years of everything points toward it, not because that era is mysterious in a vague, poetic sense, but because tracing the chain of causes backward through cosmic history eventually arrives at a moment before which the chain itself becomes undefined. What lies before that moment is the only question the universe has not yet given us the mathematics to ask correctly. If this investigation has settled something in you, if following the chain from quantum fluctuations to the first stars, to the chemistry now reading these words, has produced a question that stays with you, I would genuinely like to know what it is. Not what you think the answer might be, what the question is. Because the questions people carry away from an investigation like this are often more revealing than the answers, and the conversation they start tends to go further than the documentary that prompted it. Leave it below. The most interesting ones have a way of not letting go. Somewhere in the universe right now, and the word now carries its own relativistic complications across cosmological distances, but bear with the impulse. A star is dying. Not metaphorically. Literally. A star that formed from gas enriched by earlier stellar deaths, that burned for millions or billions of years converting hydrogen into heavier elements, is in the final stages of its life. Its core is collapsing, or its outer layers are being expelled, or its remaining fuel is being exhausted in a last quiet fading. And the elements it has spent its lifetime building, carbon, oxygen, silicon, iron, are about to be scattered into a universe that began in near-perfect uniformity, that spent its first billion years building the conditions for exactly this. That has been running this cycle, star after star, generation after generation, for 13 billion years. The first stars did this without knowing it. Every star since has done it without knowing it. Somewhere, much later, some of those scattered atoms will find their way into a molecular cloud. The cloud will collapse. A new star will form, with planets, and on one of those planets, in some configuration of chemistry that neither we nor the dying star can predict, something may eventually look up. The first billion years made that possible. It is still making it possible.